Okay, so I was talking about the solution for impedance mismatching problem. So what we are going to do is in between our transmission line and load, we are going to connect or insert a circuit. And that circuit will be known as matching, or sometimes we also call it tuning circuit. Tuning circuit, or let's call it network. So we are going to understand what is the role of this network that we have connected between the load and the main transmission line. From broader perspective, we know that I have used or I have connected this circuit so that our circuit becomes matched. So even without going into too much detail, what is the effect of this network is that now when the signal is coming from the source side, this matching network is going to transform this mismatched load to a matched load. So at the input of this network, it will appear as if the signal, the load is equal to Z naught. So what I'm going to do is I'm just going to represent this in a, it will appear as if there is now a virtual load, and that load is actually equal to ZL. So this, it will appear as Z naught. So this signal, it will find out as if it is providing power to a matched load. So at this point, reflection will be equal to 0. Because from this signal perspective, this signal find that in between these 2 points, the impedance is equal to Z naught. So what has happened, this matching network has converted this load impedance ZL to Z naught. So as a result, we get this behavior. So this is how you can understand the behavior or the operation or the characteristic of a matching network. This is what all matching networks will ultimately do. They will transform a mismatched load impedance to a matched load impedance. Because this was our problem. The problem was this ZL was not equal to Z naught. So in order to design a match circuit, what we do, we use some kind of a circuit which convert or transform, or you can call it map, load ZL to Z naught. And now we get this match behavior. Okay. Now I was talking about that, is it possible that whenever you have this situation, you can always design a matching circuit to get this behavior? No, no, it is not possible. So it means we can always design a matching or tuning circuit under a certain condition. And what is that condition? Let me write it down. as long as the load impedance ZL has a positive real part, a matching network or circuit can always be formed. So this is the condition that I was talking about. If your load that is mismatched, if you want to match it to the transmission line, you need to find out whether the load has some positive real part. So generally, load is represented by ZL, and ZL is a complex number. It has real part as well as imaginary part. So if ZL has some positive real part, irrespective whether it has some imaginary part or not, you can always find out a corresponding matching circuit for it. But if the load is having zero real part, of course, real part is zero means that your load is purely imaginary load. Your load is purely imaginary load. For purely imaginary load, it is not possible to design any matching circuit. So you can say that purely imaginary load cannot be matched. Okay. So this is the condition. Now, as I was talking about, that this matching or tuning network, this is not one network or one circuit. There are a number of types of matching circuit that we are going to explore in today's lecture and maybe in the next two lectures as well. So if you have a number of matching circuits available, so on what basis you are going to select a particular one? So also let me introduce the advantages as well. So why impedance matching is important? Why impedance matching is important? So there are a number of reasons for that. One of the reason is, of course, I mentioned that maximum power is transferred to the load. Maximum power is delivered. So if you want to ensure that maximum power is transferred to the load, you have to be concerned about impedance matching. Second reason that we are giving importance to impedance matching is it can improve. It can improve signal to noise ratio. In sensitive receiver components. And third reason why impedance matching is important can be it can reduce amplitude and phase errors in power distribution networks, such as such as antenna array feeds network. So these are, you can say, three most important reasons of impedance matching. Now coming to the selection of impedance matching network. So selection of suitable impedance matching network. So as I mentioned, many choices are available. Which we will discuss shortly. Now, if a number of choices are available, so as a microwave engineer, which particular choice you will select? So what are the factors which you take into account during your selection criteria? So factors that are important in the selection of particular matching network include the following. So on what factors, which factors you will take into account before deciding that this particular matching circuit is more suitable for your case? Okay. So the first factor is always complexity. If a given problem can be solved by a simple circuit, you will always go towards that circuit, even though there may be some other circuit available. But why you will not go for that circuit? Because that circuit is more complex. So why you are selecting a complex and complicated circuit if a simple circuit can solve your problem? So the same decision or the same criteria, selection criteria, is also used for impedance matching circuits. If there are 3 or 4 impedance matching circuits available and all of them can solve your problem, so you will find out which of the given impedance matching circuit is simple one, and you will be using that particular simple circuit to solve your problem. So this is one factor. Second one is bandwidth. So when you design an impedance matching circuit, it is going to give you the matching behavior within certain frequency range. And that particular frequency range is what we call as bandwidth of impedance matching circuit. So number of impedance matching circuits that are available to you, they have different bandwidth performance. So some are narrow band and some are wide band. So if you are designing or if you are solving a problem of impedance matching where you require impedance matching over a large bandwidth, then of course you are going to select and that particular impedance matching circuit which has wide bandwidth, because narrow bandwidth impedance matching circuit is not going to solve your problem. So bandwidth is another important factor. And of course, we will, once we go through the design of different impedance matching circuit, then we will also find out how to calculate the bandwidth of impedance matching circuit. Third factor that you take into account is implementation. Implementation. And what is the meaning of implementation? So whenever you design some impedance matching circuit, you are going to find out whether it is possible to, whether it is easy to implement that design or not. So some impedance matching circuits, depending upon the application, they may be more easy to implement as compared to some other impedance matching circuit. Of course, this is something which once you understand the theory and working principle of impedance matching circuit, then you will be able to understand this implementation. But if I explain it in a simple manner, so if you want to, if you want to design two circuits, but it is difficult to design one circuit as compared to the other one, so of course in that case you are going to go for that circuit which is easy to implement as compared to the one which is difficult to implement. The fourth factor is adjustability. This factor means that sometimes your load may be changing. Okay, your load is continuously changing. It is not a fixed load. So whenever you are dealing with such a situation, you need to select an impedance matching circuit which is also adjustable. So there are some impedance matching circuits which are not adjustable, and there are some impedance matching circuit which are adjustable. So now you need to find out that the problem that you are solving, whether it involves a fixed load or whether it involves a variable or changing load. So if you are dealing with a fixed load, then of course you are going to select that impedance matching circuit which is suitable for fixed load. But if your load is changing, then you are going to select that impedance matching circuit which can be easily adjusted for this new load. Okay, so these are some common factors that you need to take into account whenever you are in a position to select multiple impedance matching circuits, and your goal is to find out that which circuit is the best one for my applications. So now let's talk about this thing. I mentioned there are many choices. So which particular choices we are looking at? So types of matching network. The first matching network that we will look into today in more detail is what we call as L networks. L networks. This L is an abbreviation for lumped element. Lumped element. One possible design that you can use for matching a load is by making use of lumped elements. And you people already know about lumped element from your basic electrical engineering. So actually, I'm talking about capacitors and inductors. So you can use capacitor and inductor. So capacitor and inductor can be used as an impedance matching circuit. There are some advantages as well as disadvantages of L networks, which we will talk about throughout this course. But if I mention one of the limitation of L network is that they are uh, feasible only for low frequency applications. Okay. So let me say limitations. So limitation is we can't realize capacitor and inductors at very high frequencies. And by that, I mean that as a manufacturer, if you are designing or fabricating a capacitor or inductor, so depending upon what is the frequency requirement, so as frequency increases, it becomes very difficult to design capacitor and inductor. Okay, so whenever you go and find out that I need a capacitor or inductor, so that capacitor inductor uh, is going to act as a capacitor or it is going to act as an inductor up to certain frequency range. But if the frequency is more than that particular range, then your capacitor will not give you the capacitor behavior, and inductor may not give you inductive behavior. So this is kind of a limitation that if you are designing an impedance matching circuit for a very high frequency microwave circuit, then L network may not be a suitable choice. Okay. So also I need to add this term. So what L network is? It is a particular configuration of capacitors and inductors. So let in a short while this sentence will make more sense to you once I draw the circuit of L networks. Right now I'm just going through that what are the types. So one of the type is L networks, and what is L network? It involves a use of capacitors and inductor in a particular configuration. Okay. Second possible choice for matching and unmatched load is what we call as stub. So stub matching network. Stub matching network. And what is stub? Stub is a short section of a transmission line. What is stub? A short section of a transmission line which is either short circuited or open circuited. And this is something that we already covered in this course. And let me remind you, when we were talking about transmission line theory, so we consider special cases of terminated transmission lines. So we consider that if transmission line is connected with a short circuit load, what will happen to it? If it is connected with the open circuit load, so what will happen to it? So during that particular discussion, I mentioned that this is something that we will talk about in more detail when we will consider the topic of impedance matching. So this is the same thing. We can use transmission line for matching as well. But the important point is that transmission line has to be either open circuited or short circuited. So let me introduce that, or let me refer back to that particular topic that we have already covered. So if you remember, we consider this scenario that if there is a transmission line with a characteristic impedance Z0 and phase constant beta, if it is terminated with a short circuit load, so it means ZL is equal to 0. So this is a transmission line and its length is L, and we assume that this L is not very large, so that is why I've used the term short section. Short section means that its length is not very large, it is small. What we found about this transmission line is that if you consider what is the impedance behavior of this transmission line, in other words, if you uh, if you put this transmission line inside a box, so let's assume that we put this thing inside a box, and this box is completely closed, and what is available outside of this box? Outside of this box, we have these two connections. Okay, so if we measure the impedance, if we measure how much is the impedance between these 2 points, so I will call it Zn. So from our transmission line theory, we have already covered this thing, that the input impedance of this line is equal to J Z0 tangent beta. You can refer back to my previous lecture and you will be able to find out that this is something which we have covered. So if you have this section of a transmission line which is short circuited, so what is the impedance behavior of this circuit? Its impedance behavior is JZ0 tangent beta. Okay, so you can see that the impedance behavior of this line is purely imaginary. It is JZ0 tangent beta. So which of the parameter is going to change? That is L. So depending upon how much is the length of the line. So if L changes, so of course tangent function will give us a different value, and as a result in will change. So we already know about the range of tangent function. A tangent function, its minimum value is minus infinity and its maximum value is plus infinity. So depending upon what is beta L, this function can have any value from minus infinity to plus infinity. And because it is purely imaginary, so it's obvious that the the range of impedance, what is the input impedance range for this line? It can vary from minus j infinity to plus j infinity. So the important point is this line is acting as a reactive element. It can act as a capacitor or it can act as a inductor as well. If it is giving us something minus j something, so minus j something is what? If you have something like it, let me give you. If you have z is equal to minus j something, what type of element is this? If impedance is minus jx, so what is this thing representing? All of you are, I think, sleeping. I am asking a question. If z is equal to minus j something, so what is this thing representing?
Capacitive element.
Yes, it is capacitor. And if z is equal to plus j something, it must be inductor. So by changing or by varying the length of this short circuited transmission line, it can behave as a capacitor or it can act as an inductor. So in previous type of L network, we were using lumped element capacitor or inductor, the actual capacitor and inductor that you people are familiar with. But I can use a transmission line, and this transmission line can also behave as a capacitor or inductor based on this whole idea. In a similar manner, open circuited line. So if you have a transmission line where the other end is not connected with anything, so ZL is equal to infinity, and now if you put this, if you assume that this whole thing is inside a box, and then if you find out how much is the impedance at the terminal, so again, this is something which we have covered. So Z in was computed to be equal to minus j z naught cotangent beta. So again, what is the possible range of this Z in? It all depends on how much is the length of this transmission line. So by changing L, we will have possibilities that Z in is again going to vary from minus j infinity to plus j infinity. So this open circuited line can also act as a capacitor or inductor depending upon the value of L. So that is the whole concept behind stub matching network. That rather than using lumped capacitor or inductor for impedance matching, we can use a transmission line as capacitor or inductor. And by using as a capacitor or inductor, it's possible that we can design an impedance matching circuit. But of course, we will talk about this design in more detail. But this is the whole concept behind stub matching. Now, other important point is there are two types of stub matching network that we will talk about in this course. One impedance stub matching network is known by the name of single stub matching network. Single stub matching network. Okay, and the other circuit that we will talk about is what we call as double stub matching network. We will find out that it's obviously clear from the terminology that in single stub we will be using one stub to match the circuit, and in double stub we will be using two stubs to match our load. So why we will use two stubs rather than one stub? It means single stub will have some limitations or some disadvantage, and that limitation can be compensated by double stub. Okay, but right now I'm not going to talk about it. Once we start talking about stub matching network in detail, and once we go through the design principle of single stub, then I will be in a position and you will be able to understand what is the limitation of single stub. Okay. So we are going to talk about single stub and double stub under the topic of stub matching network, but I have given you an overview that what is the meaning of stub. The third type of impedance matching circuit is something which we have already covered, but not in that much detail, and that is known as quarter wave transformer. Quarter wave transformer. So what is quarter wave transformer? You already know about it, that if you have a transmission line and if you keep its length equal to lambda by 4, this quarter wave length transmission line can also be used for impedance matching. How it provides impedance matching, we have already covered about, we have already talked about that. So let me correct this one. If you remember, we represented the characteristic impedance of quarter wave transformer by Z1. Okay. So depending upon what is connected to the input. So if input transmission line, the transmission line that we want to match is having a characteristic impedance of Z0, and the load that we want to match is, let's say, ZL. So we have already proved this thing, that in order to provide matching, Z1 must be equal to Z0 ZL under the root. But there is one important thing that we haven't covered. That is, I mentioned about it in the selection criteria of impedance matching circuit, and that is bandwidth. So bandwidth performance of impedance matching circuit is very important. So quarter wave transformers can also be divided into two categories. Okay, so one of the category that we already know about is what we call as single section quarter wave transformer, and this is the one which we are looking at. So this particular circuit that you are looking at, its appropriate or standard name is single section quarter wave transformer. But there is another design of quarter wave transformer that we will discuss in detail, and that is known as multi-section quarter wave transformer. So quarter wave transformer, let me abbreviate it with QWT. So we are going to find out what is the limitation of a single section quarter wave transformer, that is this one, and how we can convert a single section quarter wave transformer to multi-section quarter wave transformer. So the main advantage that we will get from multi-section quarter wave transformer is the bandwidth improvement. This type of matching circuit will give us more bandwidth as compared to this one. Let me continue this discussion in the next session. Or I think you can take a break for prayers. So I will start my lecture after 15 minutes. Okay.